once students get connected.
So, Amit, shall I start? Yeah.
Okay, sir. Okay, sir.
Okay. I will share. Whiteboard. Yeah. So we stop here. Today we'll discuss how to apply the grid characteristic approach to obtain the numerical solution of the 1D, one-dimensional acoustic equation. We briefly discuss how to extend this approach to the 2D and 3D dimensions too. And mostly we will be concentrated on the question about the boundary condition application with the appropriate precision and how to take into account the case when we have some discontinuity in our coefficients of the equation. For example, if you have two geological layers like sandstone and maybe carbonates, so of course both of them have different p wave velocity, shear wave velocity, etc. So density. So in our equation we will have some functions like rho or lambda or mu, and this function will be discontinuous, but we will propose a method how to take into account this discontinuity explicitly, and this is the key feature of the grid characteristic approach. So I remember that we previously discussed how to describe the dynamic behavior of acoustic medium in 1D and also 2D case. What if we are now in 1D space and acoustic media for us it means that we have some steady state and we have some values of pressure near to this steady state and velocity along the or x-axis. Yeah, both of these functions are unknown right now, and they depend on the x-coordinate, on the x-coordinate and time. So the Gaussian system of equation is equal to the rho density multiplied by the dv over dt plus gradient of the pressure P equal to 0, or in our case, dP over dx. Great. This is the first equation, and the second equation is dP over dt plus rho multiplied by the speed of the wave c squared multiplied by the scalar product of the gradient on the vector v. This is divergence, yeah, is equal to 0 if we have some source. We can add here f source as a function of t, maybe x. This is external force applied to the medium, and in our case, this is dv over dx, and in our case, this is single scalar v. So we can rewrite our system as d over dt from the v and p, yeah, v and p, velocity and pressure, plus some matrix multiplied by the d over dx of this vector v and p is equal to 0 on 0, 0, or maybe if you have some force, we will add here the external force F. And matrix is equal to the 0, 1 divided by rho c squared, and 0. And we call that this is the matrix A or AX. If we will analyze this matrix, we'll realize that it has a set of eigenvectors and eigenvalues, and eigenvalues are real. So we can write that the matrix A can be represented as multiplication of matrix omega to the power of -1 multiplied by the matrix lambda and multiplied by the omega, where the matrix lambda is diagonal, and we have here c, minus c, and plus c values. This is the eigenvalues of the system A multiplied by the vector E is equal to the lambda multiplied by the same vector E. So C and plus C is the solution of this equation. And here I have to put the matrix omega -1 in columns. It has the coordinate of the eigenvectors, -1 divided by rho c and 1, and here 1 divided by rho c and 1. And to calculate the inverse matrix omega, we have to find the inverse matrix manually, and the answer will be minus rho c divided by 2 and 1/2, and plus rho c. Rho c divided by 2, 1/2. So great. This is the value of the matrix omega -1, and this is the value of the matrix omega. So let's represent in this equation. Let's introduce some new notation. The vector q. The first coordinate is equal to the unknown function v velocity, and the second to the p. So dq over dt plus, instead of matrix A, we will put here omega minus 1 lambda omega. Dq over dx is equal to 0. Let's multiply this equation from the left side on the omega. And omega is not a function of time or x right now. That's why what we can do, we can write omega dq dt plus omega minus 1 lambda omega dq over dx equal to 0. This is a 1. And if we will introduce new variable w, that is equal to the omega multiplied by the vector of unknown function q, we can put it here. Here we will obtain dw over dt plus lambda diagonal matrix dw over dx is equal to 0. This is a vector, sorry, vector 0. So let's write this system element-wise. So dw1 over dt minus c, this value minus c dw1 over dx is equal to 0. And for the second coordinate, dw2 over dt plus c dw2 over dx is equal to 0. So we know that the solution of the first equation is omega is w1 as a function of x plus ct, where c is the velocity of the propagation of waves, pressure waves, and here w2 x minus ct. Let's draw these characteristic lines, x plus ct and x minus ct. Let's look at our integration domain. We have here coordinate x, we have here coordinate time, and we are trying to solve our problem in the domain from 0 till L capital, from 0 till T capital. And what if we have some point here at some time moment and some position, x minus t is equal to constant will give us this line. This is the second characteristic line, and for w1 we will obtain the inverse sign of slope. Great. Omega 1. So we can understand what we have to set to our initial system to obtain the solution. As previously, we have to set here initial condition. First, we have to add initial condition. Initial condition. What does it mean? Some function of w1 as a function of at the time moment 0 over the whole domain x, and the same for w2. We can write it this substitution explicitly, so let's do it for clarity. W1 W2 is equal omega multiplied by the Q. Omega is here, minus rho c divided by 2, minus rho c divided by 2 multiplied by the first argument of Q is the V, plus 1/2 multiplied by the P, and here rho c divided by 2 multiplied by V plus 1/2 of the P. So if you will set somehow V and P at the initial time moment, you can calculate explicitly the value of omega of W1 and W2. Yeah. So a single initial condition is necessary. For example, for steady state with the absence of some stresses and velocities and movement of some particles of the medium, we can set V is equal to 0 and P is equal to 0. That's why both components of the vector W will be equal to 0. Yeah, but of course we can put here some initial conditions. But when we go to this point to estimate the value at this point, we have to draw again two characteristic curves, omega 2 and omega 1. And this characteristic line will go out of our domain, so we don't have here some medium. That's why we have to specify here explicitly some boundary condition on the W2 only, because the value of W1 will be calculated based on the initial condition. So we have to set here only a single. For x equal to 0, we have to set only the value of W2 as a function of time at the x equal to 0. And for x equal to L, capital somewhere here, we'll have the inverse situation. So on this boundary, we have to specify only the value of, it's my fault maybe, this is for this line, omega 2, and this is for this line, omega 1. Yeah, that's correct. Only the value of the first invariant. This component is commonly called the Riemann invariance as a function of t at the x equal to L capital. Great. So we have to specify our equation. So we have to specify rho and c inside the medium, inside our integration domain. We have to set initial conditions. This is combination of pressure and velocity. And also we have to specify two boundary conditions. First one at the left part of our domain for W2, and the second one at the right part. So how to calculate numerically the function P at the point M at the time moment n+1, and the same for V M at the next time layer. We have, I will clean here something. What we have to do, first of all, we have some. Let's now discuss the only situation inside the domain far enough from boundaries. Yeah, we have initial conditions. That's why we know P subscript M inside the domain at the 0 time moment, and the same for V. using this formula, we will calculate the values of omega 1 at the point xm at zero moment, and the same for the second invariant. Okay, using this multiplication of omega multiplied by q analytically, yeah? So we know it. Then we know that the value of the first invariant at the same moment, but at the next time moment is equal to the value of the same invariant at the previous time moment, but in the other point xm plus c tau, where tau is the time step. So we know the values of W1 on the mesh, on the grid. We will solve the interpolation problem with some predefined precision using some special stencil. For example, this one, xm plus 1, and time moment tn plus 1. This is a characteristic line. This is a c tau. So we can calculate this value, and we will obtain the value of W1 at the next time moment at the same point. Then we will calculate W2 at the same point at the next time moment using the same formula. But because we have the inverse direction of the characteristic for W2, we have to go to the left. C multiplied by delta tau. Yeah. So now we calculated both of these values, and we understand that we can write that Q is equal to the omega minus 1 multiplied by the vector of W. This relation is valid as well as this relation for any time moment. That's why, based on the value W1 m n plus 1 and W2 m n plus 1, we can go back, multiply it by omega minus 1 to calculate the pressure at the same position, but at the next time moment, and the velocity at the same position, but at the next time moment. Great. We obtained one time step. With this procedure of the updating of our data, we will obtain the time dependence of pressure and velocity over the time. The good news is that if we will do it, and if we will use here the interpolation with a second or third or fourth special precision, so the total approximation and the total convergence of our scheme for acoustic system of equations will be the same. So we will obtain O capital over the tau and h, or tau squared and h squared. So the order of the convergence used for the linear transport equations will be the same as the order of the convergence of the final acoustic numerical scheme. So one question is related to the boundary condition, and we have to deal with this if we have some discontinuity in parameters. Why? Because previously we told that matrix omega doesn't depend on the time or coordinate x, but we want to go to the other case when we have the dependency of our matrix omega. Yeah. Omega, or we can write here rho, or maybe C, as a function of X. We'll split our domain into a set of cells, and we will say that we have a node XM, and we have cell M and M minus 1, and it is possible to have the discontinuity of density of omega coefficients, but only inside the node. Yeah, we will adjust our mesh with these discontinuities, because the discontinuity is a property of the material. We know the position of the discontinuity. That's why we can do it. And inside a single cell, we will say that we have the constant material, rho or C. So this is a case of piecewise constant parameters. Piecewise constant parameters. Great. So let's deal with this case. What we will do? Initially, we will discuss how to introduce in our algorithm the boundary condition, because we will use the same mechanism to introduce the discontinuity inside our parameters. First of all, we will say that we have yeah, or let boundary, doesn't matter. Let's say that we have here x axis, time axis, the T capital, L capital. So previously we told that we can reproduce omega at the we can reproduce the value of our unknown function at the next time layer using this procedure omega minus 1 multiplied by the Q, by the W at the same time moment. Let's write it clearly. V and P, yeah? Initially V, then P, or P and V. 1 second, please. V and P, yeah? V n plus 1, P n plus 1 is equal to minus 1 divided by rho C omega 1 at some point, of course, yeah, at some point, n plus 1 minus omega 2, the W2, 3m, n plus 1. And here is W1 m n plus 1 plus omega 2m n plus 1. You have two equations here. This is the direct substitution of this matrix omega minus 1 in this vector equation. What we want to understand, this is valid for some internal point when we can calculate the value of which one? W1, yeah, W2 and W1. But what if we want to deal with this point? Yeah. From this point we can calculate only the value of W1, W2. Yeah. Oh, it's my fault. Let's check it again. W1 is for negative. Yeah, that's why we can calculate only W1. Okay, what we know. Let's analyze these formulas. What we can calculate if we want to use this formula at this particular point. W1 at this point, W1 at the next time layer will be found using this procedure and the interpolation. So we can calculate W1, we know row C and W1. What we can't calculate? We can't calculate W2. Why? Because W2 go out from our domain. So we can't calculate this. But what is it? This is a scalar, some scalar value, yeah? Some ordinary real number. But what we know at this boundary? Let's deal with the day surface condition. So once this boundary is free of any stresses, that's why P is equal to 0 for X equal to 0. This is free boundary. This is very natural when we are speaking about some seismic process. We will describe with this condition the upper boundary of our maybe very complex integration domain with some topography. In any case, this is a good approximation if we pose zero stresses on the top boundary. Great. In fact, we know this value. We know for m equal 0, we know that this is equal to 0. So let's calculate v at the position 0 at the next time moment is equal to -1 divided by rho c multiplied by the w1 at 0 n plus 1 n plus 1. This value was calculated previously minus some unknown value, and 0 is equal to the 1 w1 at the point 0 at the next time moment, we know it, plus some unknown value. Yeah, and this is some x, this is some x. They are equal. That's why we can obtain that. We can obtain from the second equation this symbol is equal to the minus w1 at the position 0 at the next time moment. So we can substitute it here and minus w1 0 and plus 1. Finally, we found how to update the values here. We have to pose that P at the position 0 at the time moment n plus 1 is equal to 0 precisely, and V at the position n plus 1 is equal to the -1 divided by rho c w1 0 n plus 1 minus minus, so plus w1 0 at n plus 1, so minus 2 w1 1 0 n plus 1 divided by rho c. This is the final answer. This is the final answer. We know how to deal with some internal points here using this algorithm, and now we know how to deal with the left boundary. If we will put here some right boundary condition with the same equation p equal to 0, we will obtain the same, but with the other sign at the right part. Sorry. So this is great. So if we want to pose some other boundary condition, for example, for fixed boundary, yeah, glued to our external very large medium, so we can pose at for example at this point the velocity at the next time moment at the point n minus 1 is equal to 0, and from this equation we will again obtain the connection, the relation between the value of the second invariant W2 and the first invariant W1. One invariant we will be able to calculate with the interpolation process, the other will be calculated automatically. So now we can pose any boundary conditions. Fixed boundary conditions, velocity is equal to 0, free surface condition, pressure is equal to 0, some non-reflecting non-reflecting boundary condition, when we say that we have to obtain only the waves that go out from our domain, and we will try to combine the value of velocity and pressure to obtain zero reflection coefficient at this boundary. This is trivial. If you want to obtain zero reflection in 1D case, you have to pose that Q at the value n plus 1 at the next time layer at the position. Okay, you can use this approximation, do d Q over dx, and the x equal to 0 is equal to 0 vector. Yeah. So this procedure also quite trivial, so you will be able to incorporate easily it in your research code. So we know how to solve the whole problem for the continuous coefficients. Let's deal with discontinuous coefficients. Yeah. 1 second. Yeah. I will clean the desk. We will split now our integration domain into two subdomains. We will introduce a single gap in our parameters at some particular node, but this procedure will be able to be applied to each node in our integration algorithm. So in fact, you can easily apply it to any number of discontinuities. What you have? You have some time axis and x-axis. This is L, this is 0, and we have here the discontinuity of the parameters. Yeah. For example, in density or in both of density and velocity. So let's say that we have left part. All parameters will be subscribed by the L capital, and right part. All parameters and values will be subscribed with R capital. And we have, in fact, two bodies. Yeah, two subdomains, left subdomain, right subdomain, or two bodies, left body and right body, with some contact here. Okay, we know that we can write in the general case that W1 is equal to the minus rho C divided by 2 multiplied by V plus 1/2 of P. And the same for W2 equal to the rho C divided by 2 multiplied by V plus 1/2 of P for the internal points. Great. Let's remember that we can write also the inverse transformation, that velocity is equal to the minus 1 divided by rho C multiplied by W1 plus 1 divided by rho C multiplied by the W2, and the pressure W1 plus W2. So great. Let's consider the left body, and for left body, we have a right boundary here. That's why we can easily calculate on this boundary the value of the second invariant, yeah, W2, because this is an internal invariant, but we don't know the external invariant W1. Now we are dealing only with the left body, left part of the medium. So what we can say, that here we have V at the next time layer at this node, for left body is equal, according to this formula, minus 1 divided by rho C W1 calculated for the left body at the next time layer, plus 1 divided by rho C W2 calculated for left body at the next time layer, and the same for pressure. W1 for the left body plus W2 for the left body. And we know how to calculate W2 left. So we will solve the interpolation inside this domain, and we will calculate W2. So we know this value. Okay. Let's look at the value of W2 and W1 as two real values. For any pair of real values, we can write the correct formula like W1 left at the n plus 1. This is the real value, non-zero, any non-zero value is equal to some coefficient alpha, subscript left, multiplied by this value, W2 L n plus 1. For any non-zero values, W1 and W2, we will be able to calculate some coefficient, fixed coefficient, right? This is true from mathematics. Let's substitute in this system, and we will obtain that that velocity on the velocity on this boundary is equal to the minus 1 divided by rho C. W1 will be lambda L multiplied by minus 1 multiplied by the W 2 L n plus 1. And for pressure at the boundary, we'll substitute here lambda L plus 1 multiplied by the same value W2 L n plus 1. what we can do, we can write the same system for the right boundary, yeah, or for the right part of the domain. Here we used only the left part of the domain, and let's use the right part of the domain. The general view is the same. We will know here, maybe with this, the angle will be different, but we will be able to calculate now W1 right. For the right boundary, we will, for the right part of the domain, this is the left part of the boundary, of the domain, the left boundary. So what we can write? We can write that v right at the n plus 1 is equal to the minus 1 divided by rho CW1 right at the next time layer plus 1 divided by rho CW2 for right n plus 1, and the same for the pressure is equal to the W2 right at the next time moment plus W2 right at the n plus 1. It's my fault, this subject 1. Great. Let's look. We can calculate W1 right. This value and this value. Again, let's write that W2 right n plus 1. This is a scalar real value is equal to the alpha with the subscript r. This is the other, not the same scalar value, real, multiplied by W1 right n plus 1. Again, from basic math, this is the correct sentence, yeah? So let's substitute it here, and we will obtain that v right at the next time moment n plus 1 is equal to the minus 1 divided by rho c multiplied by 1 second or 1 minus alpha r multiplied by W1 r n plus 1. And for pressure, we will have 1 plus alpha right is equal to the W1 right n plus 1. So we obtained two systems. Let's highlight that we will calculate this. We will calculate this with the interpolation procedure. We know all parameters. Instead of alpha r, we will calculate this one using the interpolation procedure. We will calculate this with the interpolation procedure. We know, sorry, it's my mistake. I have to write here explicitly that we have to use here the rho from the left part of the boundary, and here C again, and here rho right and C right, of course, because we are now in different medium. And again, left, 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 left. Great. Let's look at this point. Who is the owner of this point? Left part of the domain or right? The correct answer is both. So this is a single physical point. That's why we can easily write that the velocity calculated for the left part at some time moment must be equal to this velocity calculated for the right part at the same time moment. And this is value for pressure. So in any case, you can use any domain, but if you calculate the value at some point and both part of domain has this point, the values must be equal. So we will substitute here and obtain finally what we will obtain finally. VL is here. So -1 divided by rho left multiplied by C left multiplied by alpha L -1 multiplied by W2L n plus 1 is equal to the to the velocity at the right part -1 divided by rho R CR 1 minus alpha R W1 R n plus 1. This is the first equation, and the second is from pressure. Alpha L plus 1 multiplied by the W2 left n plus 1 is equal to the 1 plus alpha R multiplied by the W1 R n plus 1. So now you have two unknowns, alpha L and alpha R, and two linear equations. So you can solve it analytically for each node, for each node where you have the gap in parameters. You have to solve, but you can do it analytically. This is a linear system that contains only two parameters, and obtain these parameters, and you can update values of the V and P at this point at next time moment using any of this system, because you will obtain the solution. So you can use this or this, the answer will be the same. So in fact, now we solved our contact problem explicitly. So we obtain the correct procedure to deal with this situation. To simplify the formula, you can use the new notation impedance, left or right. This is the rho left or right multiplied by the C left or right. If you will add this notation, you will simplify the final formulas. Let's stop here, and I will share with you the anaconda. 1 second. Repeater lab, and I prepared for you one new notebook to play with these formulas. So initially we start with the continuous coefficient case. So we have the matrix A. We have a single parameters rho and C, because now we don't have any discontinuities in it. This matrix has two different eigenvalues, -C and C. For -C, we have this eigenvector. For value C, we have this value of the eigenvector. So we compose the matrix lambda. This matrix is diagonal. We can compose easily, row by row, the value of matrix omega minus to the power of -1. We can analytically calculate the inverse matrix to obtain omega minus rho C multiplied by 1/2. So we can check this that A is equal to the omega -1 multiplied by the lambda multiplied by the omega. So this is a correct representation of our matrix A. So then I used the NumPy to describe current time layer and next time layer. In both arrays, we have two values one for the velocity, one for the pressure. I implemented the function that apply this matrix multiplication. So if you call omega inf and put here the values of W1 and W2, you will obtain the value of V, velocity, and the value of P as a result of the multiplication of the matrix omega, analytically known, on the vector of invariance W. So you can check this formula and compare it with the result of multiplication of the omega minus 1 on the vector of W1, W2, row by column. So this is the trivial function. The same for omega. If you know the value of V and P, you can obtain the value of W1 and W2. So you can go to the Riemann invariance and back. I applied the initial condition here. In fact, I choose V and P such that one of the invariant W1 or W2 is equal to 0 in the whole domain, and the other is not equal to 0. It will lead to the initiation of the plane wave propagated to the right direction or to the left direction. It depends on the chosen number of invariant W1 or W2. I introduce some mesh, and each time layer I go from the left to right in our domain. Initially, I calculate the values of invariants W1 and W2 at the current M point. Then, if now we are inside the domain, we can calculate the invariant for the previous point and for the next point. If we are outside of the internal point, so for example, at the left border, I decided to use the periodic boundary condition. So if we want to go to the point from 0 to the point -1, we can go to the last point in our array, m capital -1. This is the natural periodic boundary conditions, and the same is valid for the right boundary. So in this case, we will have the wave that propagates from left to right and many times loop over our integration domain. Here we have to solve our linear transform equation for the value plus c and minus c, and eventually using W1 and W2 at the n+1 time layer, we calculate the values of velocity and pressure at the next time layer n+1, and then we simply copy the next values of P and V to the current. Or you can swap the pointers to the next and current arrays to reduce the computation time by 2. It's up to you. For simplicity, I used this naive implementation. You can see here. Initially, we have here discontinuous initial conditions, rectangular. But due to the fact that we use grid characteristic method, it is not a big deal for our method, because this discontinuity will go through the characteristic line. So initial pressure value and final pressure value. After some time, we can see the P wave propagated to the right. Some portion of this wave go back from the left, and it's obvious. How to add the acoustic source? In fact, it's very trivial. So I chose some frequency, and if we have a right part in our equation, we have to use some numerical scheme, some time stepping scheme to solve ODE. I use the explicit Euler scheme with a small time moment, with time layer, because the precision of right now we used the interpolation with the first order of precision it will be enough. So I simply add here one step. I added a source. So if currently I calculate the value at some position, I simply modify the value of the pressure, adding the source multiplied by dt. The special order of this procedure is O over the T, O capital over the T, the first order. And you can see here we don't have some initial conditions, and you can see the initiation of some waves inside the homogeneous medium. And finally, if we are speaking about this continuous problem, you can see here all mathematics that I explained previously with the whiteboard. This is omega at the left part. Then I substitute with unknown value alpha left after alpha left. Here the same for the right part, and again substitute. And coefficients will be found with this big formula. So we can update the velocity and the pressure at the next time moment easily. So I implemented this here as a tiny program. I simply added the new function solve discontinuity, where I put the value of W1, calculate for the right part of the domain, omega W2, calculate for the left part of domain, and I added here the discontinuity. I think, yeah, 1/2. In the middle of our domain, we have discontinuity. From the left part, we have rho is equal to 0.3. In the right part, 0.5, and the same for C. So I calculated omega. Using omega, I calculate the necessary W1 and W2. Then I applied the interpolation procedure for the necessary W1 and W2. And then I simply solve discontinuity at each node. So you can see the special distribution of the P.
Sir, we are not able to hear you, sir.
Sir, please unmute your device.
Okay, and now can you hear me?
Yes, sir. Yes.
Oh, great.
Yes, sir. Yes.
And can you see the anaconda? The anaconda, yeah. Can you see the code? Yeah.
Yes.
Great. So
yes, sir.
Finally, what I have to say that if you have some discontinuity, we can apply this procedure that I described, and you can see the transient wave, yeah, with some velocity. Initially, we have some pressure value and some velocity value here. After some time, we have the transient wave, and we have the reflected wave. If you will compare the solution with the analytical coefficients for reflection and transmission, you will obtain the good agreement. So I put here some task. So try to change the initial condition and try to run the simulation, and you can use the improvement from the first order to the second order scheme, and you can obtain the better precision with this procedure. Now we can stop. This is the full material that I want to cover, and only we will have only one more lectures next week. And I asked my master student Alexei Shevchenko to prepare the material and describe explicitly one approach how to improve the precision of the scheme without the extending of the special stencil. Why it is important? Because if we are speaking about the situation when we have a single discontinuity, and if we have a narrow stencil that includes only two nodes, special nodes, we can deal with this discontinuity. But if we will introduce one more node here, we will be in the situation when we want to interpolate some function on the special stencil, but this function unfortunately has the gap in the first derivative. As far as you understand, it is impossible to interpolate with enough precision with some polynomial the function with discontinuity, or the function which derivative has the discontinuity. So we can go to the other direction and fix the same stencil, special stencil, as in the scheme of the current Isaacson Rees, but using the extension of our system of equations, adding some derivatives. So thank you for your attention. I hope that Amit will share with you this record, and
Yes,
I
sure.
will update the material right now, and I share with you this Python file so you can try it at home. Thank you very much.
Thank you very much, sir.
So goodbye.
Goodbye, sir. Goodbye.
Thank you, sir.